Here as a representative of a large group of people who have me perform what as shown today. They're all from Central Europe and from Italian and from a hard metal making company and also Spanish speaking in Europe. Well, that's the covered called hard metal. What is that? I'll show you, of course, why I wanted to do what I did and how I did it and what I want to put my results and conclusions were. But let's jump right into it. So I'm interested in milling tool damage, subtractive manufacturing, so to say. So chips are formed that fly away, and the tools that are used for that are usually dull knives, so to say, that are made of a composite material of tungsten carbide, ceramic phase, and coated binder metal. And their damage initiation in hard-coated state, for example, or elevated temperatures are not currently well understood. That's the main motivation for my work that I did. And what I want to point out is that the thermal loads that are acting at the cutting edges of those milling tools are highly concentrated, spatially and temporally. And we looked closely at this, and what we found out was that these temperatures that act at the cutting edges of such milling tools, you see here a 2D cross-section of that, are distinguishable from other situations by FEM simulation studies where we put in thermophysical and thermophysical properties as a function of temperature of hard coating substrate material, the tungsten carbide total hard coating that I talked to you about today, and the workpiece. And what we get out from this is, so to say, the temporal evolution, spatial evolution of temperatures that act at the cutting edges, and those are of interest because they were not as high as expected for milling, and especially they're in the temperature range of 1 to draw H2 of about 600 to 700 degrees C. And what is also interesting is that the associated stresses that we also looked into in detail are higher than thought by colleagues before. So around 1,000 megapascal and above, slightly above. And this is of interest, and what was the motivation for works that we did to find out that cavities and pores accumulate in laboratory experiments, and that the cutting edge, we will cutting edges to become crack precursors at those cutting edges at conditions that I'll show you today in experiments in more detail. Alright, so we'd like to understand more closely what's happening at the 700 degrees Celsius, 1000 megapascal range in these materials at around 700 degrees. That's where engineers are interested because they want to know how to load their tools more highly and still do good cutting, decent cutting job in industrial applications. So the investigated material was this tungsten carbide called hard metal material with an average size of the tungsten carbide crystallized in ceramic hard phase of about 500 to 800 nanometers and 12 mass percent metallic binder. And very importantly, it's this, all the specimens I'll show you today are made of one and the same manufactured materials, so we can assume a constant defect population that is present prior to loading. The specimens we used were of an hourglass shape with 6 millimeter in diameter at its minimum. The shape was used to avoid buckling in those uniaxial compression and tensile tests we did at 700 degrees C that were performed in this vacuum chamber of a servo hydraulic testing device to avoid specimen oxidation at the test temperature of 700 degrees C isothermal conditions. We also did FEM modeling of our specimen to understand its loading rather well. We did that with these conditions here. You can find those details in the paper. I'll point out to you later. We parameterized the material models we applied to understand our deformation behavior of our specimen using cyclic experiments and creep experiments with a stepwise increased loading fashion, all at 700 degrees C, as pointed out here with this image. What we applied was R-1 loading and monotonically increasing load. We did that until fracture, and also we did perform stop experiments to look at the microstructure before fracture. Alright, so details here I'll give in the paper. I just wanted to point out we did perform a certain, as the previous speaker pointed out, we did perform 30 experiments at certain stress amplitudes to see have a statistic parameterization of what is doing, so say statistically meaningful information. We documented the fracture surface structure and the nature of origins of fracture, and we determined effectively loaded volume of our specimens loaded onto the fracture at R0 and then R-1 close to the peak limit. What is this effectively loaded volume? It's a way to assess the failure probability of complexly loaded structures, because bodies of the same defect population and same VF show the same probability of failure, and the same this VF can be for very simple load cases, it can be determined analytically, and for complexly loaded specimens that may even form plastically during loading, you can evaluate it numerically. That's what we did. It's basically a weighted sum, so to say, of contributions to the probability of failure of a certain structure on arbitrary loading situations. Okay, so the results, what were they? We saw a certain distribution of fracture stress at elevated temperatures with a certain characteristic strength with a viable modulus of 35, which is rather high for this class of materials, I'd say. And we looked at the fracture origins of 13 of 30 specimens equidistantly chosen in probability of failure. And we looked at one of the microstructures that loaded until a probability of failure of 10% of fictitious probability of failure, and looked at what we see in the microstructure to find out maybe why we see what we see here. Because the fractured specimens, they show for the lowest fracture specimen, lowest fracture strength specimen for the highest. I'll show you examples. We see only above average sized tungsten carbide grains, which is very unusual for this class of materials, because usually for these large specimens you find non-enthalpic inclusion and force at the origin of fracture. So this was baffling, and we thought, well, what can be the reason for this? The very reason, if you look at the virgin material, is, or I'm convinced of that, is that you find defects that form in situ during loading, or it's cavities that then coalesce to become the main dominant fracture mechanism on these kind of loading conditions. So if temperature and stress is high enough, that happens. Under monotonically increasing load, and it's also the case under R-1 loading, if the combination of temperature and stress amplitude is high enough or sufficient. You see here again the R-1 loading, R0 loading case distribution here, and then what you also see if you look at the SN, so to say, curve, you find that it's a rather low scatter, which is also very uncommon for this kind of large specimens in this class of material. But it's also interesting, didn't bring the stress strain hysteresis curves for you, but please look at the mean strain and think of it as an elongation of the specimens that happen when these cavities accumulate and don't fully close until the compressive half cycle, as the Pichler has proposed. And you see the kinetics of these mean strain shifts, so to say, are higher for higher stresses. But I want to draw your attention to this individual scatter within one stress amplitude. And this has to do, I think, with small microstructural differences. And this is also relevant for fractography, as I'll show you in a second. For this load case here, with say close to the fatigue limit, 1,100 megapascal stress amplitude. And what we see here are porous aluminum-containing inclusions, and again, also these above average size tungsten carbide grains at the origin of fracture. So far, so good. What is interesting is that the ranking of the cycles to failure doesn't really correspond to what we see on, or what we expect to see at the origins of fracture. You see here, well, we have pores, non-tungsten inclusion for the pores of an individual class of defect in the fracture origin. We see that the commonly observed ranking of, say, large NF and smallest defect is not given anymore. If you compare those two here, this one here is smaller than this one. So something else has to influence the NF ranking, which is, I think, small variations in cobalt in the vicinity of those defects. You see here, you don't see so good here, but you see here there's a lot of cobalt binder accumulation in the vicinity of this defect, which makes it fade earlier than this here, which has an order of magnitude more NF. And if you look at the next class of defects, which you could argue, okay, this has a different stress concentration factor because the chunk is smaller, the shape is different. Still here, you see the aluminum containing inclusions, the size ranking doesn't really correspond to this expected inverse relation between NF and size. So I think the coalescence of pores that emerge here plays a role, and I can maybe convince you by showing you this here. We looked at unfractured specimens that we stopped before fracture, and what we see is, okay, we have a certain amount of small pores that have a certain size, right? We looked at the size of those, classified them. Now defects in between 0 and 100 nanometers in maximum dimension or extension, micro defects that were in between 100 nanometers and 1 micrometer, and defects that were above 1 micrometer in size. So when we categorize them, count them, and plot them here, the defect number per unit area, load cycle count, and applied stress amplitude, we see the nano-defects compared to the virgin material. You see here, this is the nano-defect symbol. They rise with both quantities and kind of, what is it called, setting, they reach a plateau. Because you saw maybe in the previous image, they kind of, every site at some point has the, every site where stress concentration is rather high forms such a nano-defect at some point. So there's a saturation in this number. But more interestingly, maybe here for the given sizes we looked at of the area, you see here a rise with micro defects. So nano-defects merge to become micro defects. And for the defects, we didn't really have representative areas, much other areas we looked at. But still, it's interesting that these defects, they become large in number and may really play a role in this fracture processes, in these conditions relevant to the tooling I mentioned earlier. And also very interesting that also supports this idea is that effectively loaded volume, and I mentioned before, if we evaluate it numerically for the specimen, does change during loading for monotonically increasing situations. And if we consider that the stress distribution changes during loading due to classification, you see here a mesh size independent representation of the contributions to BF is, I think you can imagine here in the beginning, your stress concentration on the notch root, so to say. This here is on the notch of a radius of 50 millimeters in our specimen. And due to classification and residual stress buildup, you have an increase in this BF. And if you consider that the effectively loaded volume is a function of stress at fracture, then you can, if you remember those results here, sigma 0 was about 2,100 something. If you go on here, you can read here this blue is the maximum principal stress, and you have to correlate it with this point here. That's why I drew all those arrows to make it more readable, so to say. Stress at fracture, go here, and then you find out it's about 50 cubic millimeters. That's lower than the room temperature with no classification before fracture. And this here, this 50 cubic millimeters, is a value larger than for the case of R-1 loading, where you have less classification and also therefore less effectively loaded volume. It stays in that region. Remember, I told you before, it rises from this region here, and the case of R-1 loading due to the lower stress amplitude kind of stays in this region. So one would assume that this lower effectively loaded volume would be a smaller net, so to say, in which I catch fish in the fish pond, so to say, and I should find those in the bigger effectively loaded volume, those defects that I showed you earlier. But this is not the case, and I think the reason why you find only the above average size tungsten carbide grains in those cases with monotonically increasing load is that tertiary creep happens at the fracture stress, close to fracture stress, and that's why small variations in this minor content or above average size tungsten carbide grain zones in the sample, they become then the most dangerous spot in the specimen to fracture. And this is, I hope I could convince you that that a combination of temperature and stress exists for this material class at which the transition from ceramic-like behavior to more metal-like behavior occurs, where pore coalescence, so to say, determines or becomes the fracture fracture kinetics dominating factor. And this is something that is very much of interest to the tooling industry. People want to make their tools load more heavily so they can finish their milling jobs earlier, and they have a competitive edge over their big lighter or over their competitors. And this is something that is interesting in my eyes because the size of the interior defects play a role for large effectively loaded volumes, low temperatures, and that's a lot of applications of those material class hard metals. But the kinetics of the coalescence support that form the reloading are important for small effectively loaded volumes. And if you consider we've done unpublished work on the effectively loaded volume of real milling tools, they're very small because the temperature where is high, but the temperature is high at the cutting edge. You see only very small effectively loaded volumes in the order of magnitude of a couple hundred cubic micrometers. So this is, I think, very crucial to understand when we try to improve milling tools performance. If you have questions, I'll be happy to discuss.